All right. It looks like we have a few more people that accepted and should be coming, but I feel like we can probably kick it off now, Kelly. What do you think? Yeah. Okay. Well, hello everyone. Welcome to the Wave Energy Converter Simulator or WEC Sim Software Demo Day session. I'm Megan Anderson. I'm one of the primer software demo days points of contact. And Swara, would you like to say a few words about this series as our DOE program manager?
Yes, thank you so much, Megan. By the way, can people hear me?
Yes.
Okay, great. Apologies, y'all. I've been having some difficulties with my machine this week, which is also why I'm not on camera. But anyway, thank you all so much for attending the second of our Software Demo Day series, where we hope to increase awareness of these various software, demystify how these software function, and ultimately foster cross collaboration in marine energy software development. And I just have to say, the energy from our first event and to now and going forward, it's been so palpable from the get go. And we thank you all so much for being part of this series' success. And we hope that you learned a great amount about Primer in the first of these events. And if you were unable to make it, we have a recording available and we will have going forward for our Demo Day series. And yeah, for years now, WPTO has funded various software in the marine energy field. And we want recipients of our funding to learn more directly from each other. And today we're going to be learning about WECSIM, a wave energy converter simulator that has a vast variety of applications within and outside the wave energy field. And for now, I'll just pass it back along to the primer and then to the WECSIM team.
Great. Thanks, Swara. Next slide, Kelly. All right. So we actually kicked off this session a couple weeks back with the primer team. Obviously, today we're talking about WECSIM, and the next session is open fast on Wednesday, April 23rd, 11 a.m. Mountain, and we'll talk more about that later today. Next slide. All right, so we'll be hearing from Kelly Rule of Sandia and Mohammed Shabara of the rest of the Sandia team is made up of Dominic Forbush, Adam Keister, Jeff Grassberger, and Jorge Leon. The Unreal team is David Ogden and Sal Hussein. And aside from the team members, there are loads of other contributors that, made an impact on WEXIM's success. All right, and with that, I'll hand it off to the WEXIM team with Kelly and Mohammed.
Thank you so much. We're really looking forward to kicking off the Software Demo Day series with a WEXIM demonstration. It'll be led by myself and Mohammed. I'm going to start out by talking a bit about what is WEXIM and what WEXIM is and how we use it. And then I'm also going to talk about how to access WEXIM. Then I'll pass it off to Mohammed, who's going to talk about how the source code is structured and the workflow. And then he's also going to go through how to run WEXIM with one of our examples, which are one of the out-of-the-box examples that just work once you have installation. And then both Mohammed and I are going to talk about some of the example applications of WEXIM. So within that, we're going to be pivoting from just it being a presentation to going back and forth to actually running the software. And just for clarity, this particular demo is not one that it's required for you to have anything installed to follow along, but if you do have WEXIM installed, you are welcome to follow along. Our notional schedule is that we have about an hour to give the presentation, and then we have 30 minutes at the end for Q&A. That's a notional schedule where we can be flexible on that. So we have an hour and a half total. All right. So I'm first going to talk about a little bit about what WEXIM is. So WEXIM is actually called, the long form is Wave Energy Converter Simulator. It is a joint Sandia National Laboratories and National Renewable Energy Laboratory project that has been funded continuously by the U.S. Department of Energy Water Power Technologies Office. So many of you on the call, thank you so much for joining. But yeah, so WPTO is our primary funding agency or sole funding agency for this work. The software simulates wave energy converter dynamics and performance in waves. But I hope one of the things you'll take from this presentation today is that while the software is nominally called WECSIM and our initial scope or our intended use case is for wave energy converter dynamics, it is in fact a floating body, multi-body dynamic solver that solves the equations of motion in the time domain based on the Cummins impulse response function formulation. So that means that the same framework, the WECSIM software framework, can actually be applied to many different floating body systems. So while our scope and funding is focused on water power and marine energy applications, you'll see that people have adopted this open source software and applied it to use cases beyond what we had originally even intended or envisioned possible. So that is one of the benefits of open source software. While WECSIM is open source, it does have paid license dependencies. So we are built on top of MATLAB and Simulink. So MATLAB and Simulink are MathWorks packages that are paid for packages, but our source code is still freely available. The software is released on the WECSIM GitHub repository, which I've provided the link there. And a note is that it's an Apache 2.0 open source license, which means that this is a permissive license. People can take this software and they can privatize it, make a private repo, and modify it and use it to their own needs. And we have plenty of examples of both people in industry, technology developers, academics, consultant companies who have their own forks of WECSIM, essentially. So for a little bit of history, our project started in 2013. Our first software release was June of 2011. So we've been doing this for a long time. And our most recent release is 6.1.2, and that was in January of 2025. All right, so I think it's really important to provide a little bit of context about where WECSIM falls within your computational time versus model fidelity framework, we can call it. So, on the x-axis, we have low to high fidelity models going from frequency to time domain, nonlinear potential flow, RAND, and LES in terms of model fidelity. And then on the y-axis is computational time. And so, you've got your low order models that are based on linear superposition. They're based on potential flow theory, inviscid irrotational flow with small amplitude motion. So those are pretty limiting assumptions when you think about their role in wave energy. So, but they're run really quick. So they're really great for shape optimization. However, for complex multi-body systems with power takeoff systems and control, those linear frequency domain models are very limiting. And there's a lot of literature out there that talks about why applying those types of tools without sufficient numerical or experimental data to validate them is really hard. The same is true once you move kind of one step up into those linear time domain solvers like WECSIM. You've got almost real-time computational time, although WECSIM typically runs a bit faster than real-time, quite a bit faster than real-time. But once you move into that time domain, you're allowed to start adding some nonlinearities. So I like to say you're adding realism back in the model. People can debate that because you need to have those tuning coefficients or those nonlinear parameters often need to be calibrated or tuned with higher fidelity models or experimental data. So the benefit is that once you have moved to that time domain, you can start to add some nonlinearities in, and you can do it pretty quickly in terms of computational time. The downside is you really have to have relevant data to properly tune your model, or else you've got some of the same restrictions of those linear frequency domain models. So we can run things quickly. You can add some, nonlinearities in, and Mohammed will talk a little bit about some of the nonlinear features and how they compare to some higher order models later in the talk. Okay. Why use WECSIM? So it simulates the dynamics of devices that are comprised of both rigid and flexible bodies, power takeoff systems, and mooring systems. So each of those components there, bodies, PTOs, moorings, those are actually library blocks that we have within the WECSIM software that you can drag and drop into your model. A really fundamental theoretical understanding of WECSIM is that it is based on its hydrodynamic coefficients are derived from those frequency domain boundary element method solutions. So those are those, linear frequency domain models like WAMET, Aqua, NEMO, Capitaine. So we take those coefficients and we turn them into their time domain equivalents. But the base assumption is that that frequency domain boundary element method hydrodynamic data. But as I mentioned, we're able to solve these, develop the equations of motion of these complex multi-body systems by moving into the time domain and solving those governing equations of motion for each body and constraint and joint in 6 degrees of freedom. So in the bottom, you have a nice little workflow that kind of demonstrates this is kind of what your process would look like within WECSIM. So you start with your device specification. That's typically in the form of a 3D CAD model. So that's that's from SolidWorks or Rhino or ANSYS. There's a lot of ways you can develop that geometry specification. And then you add in the relevant numerical methods, the multi-body dynamics, the hydrodynamics, the PTO, the mooring, and that's done within WECSIM. And then on the right-hand side, these are some of the types of data that we can get out of WECSIM. You can get things like your motion response, your forcing, your power. You can even populate a power matrix. So that's at a high level what WECSIM is and what it does. So these are some of the applications of WECSIM that I think people may or may not be aware of. So on the top left-hand side, we have electric power generation applications. So when we were originally scoping WECSIM and thinking about use cases for WECSIM, that was our primary use case. You've got waves, you're moving the waves are moving a body in water. That movement is driving a generator of some form and you're producing power. That's the typical use case. But more recently, we've seen applications of WECSIM for wave power desalination and floating offshore wind. And we'll talk a little bit more about most later on and how WECSIM can be used for floating offshore wind. Additionally, we've seen WECSIM used for wave-powered aquaculture. So, WECSIM is used to model those floating body dynamics of the wave energy converter, and it's also used to model that aquaculture system. In this case, it's an upwelling pump. Additionally, it's been used for vessels with crane operations. This bottom left-hand image is a really interesting work that's come out of some researchers in Japan, where they've got a vessel, they've got a crane, and they're trying to move things from that vessel onto another vessel or move around in the vessel. And so WECSIM can model those types of complex multi-body systems with floating body dynamics. Furthermore, on the top right-hand side, you can see an application of WECSIM, again, not by us, by an external team, where they actually used WECSIM to simulate the installation of floating offshore wind towers. So they were simulating these floating platforms that are used to install these large offshore wind farms. And we've also seen applications of WECSIM that are based on using WECSIM to model underwater vehicles. In the previous page, I had a citation there. We actually drafted a review paper recently that highlights some of these atypical applications of WECSIM. We call them, beyond wave energy. Okay. In terms of accessing WECSIM, the software requirements are that you need to have that pre-processing computer-aided design software. So that's that CAD software. That's what's going to be used to create your 3D geometry. And essentially, that 3D geometry is then meshed, and then it's a surface mesh, and then it's run in a boundary element method solver. The boundary element method solvers we have listed here are the ones that are currently supported by WECSIM, although that is not an exhaustive list. There are plenty of BEM solvers out there. Similarly, that same data that we extract from the boundary element method solution, that could be obtained through CFD, that could be obtained experimentally. We also support those methods. However, our primary workflow is the one highlighted here. To access the WECSIM software itself, we host the software on the GitHub repository. The link here is to where you would actually access the software. And as I mentioned, we have some required MATLAB toolboxes. So we require MATLAB, Simulink, Simscape, and Simscape Multibody. The latest compatible versions of those toolbox requirements that we support are provided in the table on the right. We, on occasion, will upgrade the oldest compatible version, but currently we support 2020B version of MATLAB. Additionally, to process that boundary element method data, we have a package that we call BEMIO, the boundary element method input-output parser, that is actually included within the WECSIM source code. So that basically takes that boundary element method data, converts it into a form that's readable by WECSIM, and then we run our models. But Mohammed will talk to you a bit about that. So additional optional software requirements. So these are applications that we think of as, we call them advanced features, but you could really call them anything. These are ways that once you run a WECSIM model or you want to couple a WECSIM model, you can add some complexity. So if you want to create a really nice visualization of your WECSIM model, you want to show the wave surface elevation moving or the pressure glyphs on the surface of the body, things like that. We have coupled WECSIM with ParaView, so you can use ParaView to create these really nice graphics. We've got some videos of that on our website. You can also couple WECSIM with Moordyne to have more complex mooring system modeling. And we'll have a talk on Moordyne as part of this series. It's May 7th at 12 p.m. Mountain Time. So if you're interested in learning more about Moordyne and how it can be coupled with some of the software in this series, I highly recommend you attend that. We also have the option of parsing both input and output data for WECSIM with MHKit, and that is also featured in this series, May 21st, 12 p.m. Mountain Time. In terms of accessing the software, like I mentioned, we have a GitHub repository. We have an organization that's called WECSIM. So it's github.com/WECSIM. You'll see a collection of repositories in that organization. One of those we call WECSIM, which means you go to github.com/WECSIM/WECSIM. That's our WECSIM source code. So that's what you actually need locally to run the software. And then we have a WECSIM applications repository, which has a suite of a whole bunch of different applications beyond our basic examples. And Mohammed and I will highlight some of those applications there. So we maintain a suite of some of what we call those advanced features, all of which is publicly available. We also have online documentation, also hosted via GitHub. We have, a user manual, a theory manual, a developer manual, and a whole manual dedicated to most. And that includes information like recommended citations, our license, some of the theory that's behind WECSIM. We even have a whole online training course. We have both the slides and pre-recorded presentations there. So there's a wealth of information there. And whenever we get questions about WECSIM, we typically redirect people back to the documentation because typically that answer is found there, but it might not always be easy to access. Furthermore, if users have questions or feature requests, they can submit what's called a GitHub issue, and our team maintains these issues. To date, we have over 1,000, I don't remember the actual count, of closed issues. And additionally, we have the opportunity for users to submit pull requests, which means that they can submit modifications to the WECSIM source into the main repository. So those are our primary ways of interacting with our users. And with that, I'm going to pass it off to Mohammed.
Hi. So I'm going to start with the code structure. I'm going to share my screen in a second. So the code structure. So I will start first with an intro of what is a perfect software to be able to simulate a wave energy converter. And basically, I would like to echo George Box Coate, he's a British mathematician, said that all models are wrong, but some are useful. And basically, in order to simulate the wave energy converters, you would need to use some models and also need to know the limitations of these models in order to get an accurate representation of your device. So in a perfect world, you need to have a tool that can do a wave to wire. It can take the energy flow from when it's still in the waves up to it goes to a generator. And the first step is to have a wave resource, which is in our case can be the MHKit or any other tool out there. It gives you the incident waves, the wave directions, the wave spectrum, and the stuff that's going into the device. And then we also need to have some hydrodynamic solvers that can take this inputs from these wave resources and then compute the forces or the coefficients that are needed. We have the low fidelity, empirical, numerical models, CFD models. There are multiple resources out there. And then we need to have a tool that does the dynamic simulation. And in that case, we have the WEC sim. The WEC sim can do calculate the hydrodynamic loads, can also account for the effects of the mooring forces on the device, can also do some calculations related to the hydrodynamics. So the WEC sim kind of goes into these two blocks, the yellow one and the green one, but it's mostly heavily on the yellow one. And then we also need tools that can do some structural dynamics, can compute the fatigue, can do the FE analysis and get the forces on the device components. And also we need to have tools that can simulate the particle unit and the flow of power from the device up to the generator in a hydraulic system or electric drive or a turbine. And this is pretty like there's a rich of toolboxes in MATLAB, and this is something very unique about the WEC sim because you can pull any MATLAB toolbox that you need and integrate it into the WEC sim or the Simulink model to get whatever you're looking for. And then you have the power generation and the grid. So the WEC sim goes into here, the hydrodynamics as a WEC sim, and then also the system dynamics, and also goes into the mechanical power transmission. You can couple it with the MHKit for the wave resource. There is now a MATLAB version for the MHKit, and also there are some tools on the MATLAB built-in tools that can do fatigue analysis, can do FEA analysis, and stuff like that that can be coupled into the WEC sim, and so on. So this is like a summary of the WEC sim. There are plenty of boxes there, and it's pretty distracting. So we will try to go through one of them at a time or step by step. So in order to simulate or to use the WEC sim, you need first to have a CAD, the geometry of your device. And also after having the geometry, you need to get a good mesh. And this is pretty time-consuming part. You have to know what is the good mesh and how BM solvers handle this mesh. So you pass this mesh to the BM solver, Aqua, Nemo, Capitaine. Also, WEC sim supports the development in Capitaine, but we won't be going there in this presentation. So you generate your hydrodynamic results from this BM codes. You pass it to BMU here, which is also part of the WEC sim repository. It's a pretty simple and useful tool. This BMU function will generate a standard file called, it's an H5 file, a binary file, that has all the inputs needed in the correct format for the WEC sim. So you don't really interfere with much of the details there. You just generate your hydrodynamic results from WAMET or Capitaine or Nemo and pass it to BMU. BMU will generate this standardized formula for you. You can also use Moordyne, the coupling between the WEC sim and Moordyne is very simple. We have a team member who's called Jeff. He did a pretty good job there to make things very easy to the users. After you have this preparation done, before you start working on the WEC sim, you start building your own WEC sim model. The first step to build a WEC sim model is to have a Simulink model. It has basically the bodies that you have, the reference frames that you want to use, the constraints, the particle unit. You start building the blocks and connecting them together the way that physically reflect the model that you have or the device you have. After having this first WEC sim step, you can go to this next step, which is creating the input files and defining the parameters that are related to the box defined in the Simulink model. After that, you run the WEC sim. The WEC sim, just write in the command window WEC sim and then press enter, and this automatically will trigger a sequence in the background. This sequence, this sequence will start first by reading the input file here, and then we'll take this input file and try to match it with the Simulink model that you did. If they didn't match, it'll give you an error, and then automatically it will start doing some post-processing depending on the variables or the functions that the user defined. So if you want to look at certain power output of the device, or you want to look at certain force or the trajectory, velocities, accelerations, speed, this will also be done automatically, and then you will get some outputs that the user requires. So I kind of went through it real quick. I'll open the WEC sim in a second and show you an example case. The example case that I will show is an RM3. The RM3 is just two-body problem. One that's allowed to move in a 6-degree freedom fashion, and the other one is allowed to move in a heave-only motion with respect to the this power here. And as I said, the first step in the WEC sim part, after getting the BIMU and all these things, is to build the Simulink model. As you can see here, we have two bodies. Just drag and drop. Go to the menu here, go to bodies, drag and drop two bodies, and then you have a translation connection between these two bodies. You drag and drop another block, and then the other one for the spar with the global reference frame, which is here. So, and then start connecting stuff together. I will swap now to the WEC sim itself. So when you download the WEC sim from the GitHub repository, you will have this these folders. In order to be able to run the WEC sim, I'll couple it to your MATLAB. You just need to open this, add WEC sim input file, and run this this function. Pretty straightforward. The thing is that every time you open MATLAB, you will need to rerun this. There's another way that you can just make it automatically, the paths automatically implemented in the MATLAB, but through the startup folder, so that you don't need to run this model every time, but we won't go there right now. So once we have this done, you will find there's a folder here called examples, and this is probably, as a user, you don't need to go through the rest of the folders. Just go to the examples. You'll find multiple examples. One of them is how to use BIMU. This is, for example, of WAMIT and single body problem. WAMIT will generate a .out file. This .out file, you put it here in this repository. That this is the .out file. This is the only output you need from WAMIT. You run BIMU, and it will generate the required H5 file. After you're done with your BIMU, you will go to the RM3 example. The first thing is we need to define a geometry, and this geometry is used for two reasons. One of them is for visualization. The second one is to compute some hydrodynamic forces if needed, and this is not always needed in all the simulations. So you can just have a geometry file. The resolution of the mesh in this geometry file is not important for most of the cases unless you are using an advanced feature. So here we have two bodies, the geometry for each one of these bodies, and then we have the hydro data. It has the .out file from WAMIT, and we already run BIMU, so we have the H5 file right there. So once we have these two things in place, the H5 file and the geometry, we can go ahead and open the WEC sim input file itself. So if you go here to examples, RM3, and go to the WEC sim input file. So these are the inputs that you need to define. It's something that are some inputs related to the simulation, some inputs related to the waves, and some inputs related to the bodies that you have, and then the constraints and the power takeoff unit. For most of the simulations, you won't need more than that. Let's go take a look at the Simulink. So before going into the WEC input file, you go to the Simulink. You have here, this is the WEC library. You have body elements, cables, constraints, frames, moorings, and so on. The most used one would be, of course, the body elements. We have flexible bodies and rigid bodies. And we will go into the flexible bodies downstream in this presentation. So you just drag and drop like this, as simple as that. And then you start connecting stuff. So it makes building a WEC pretty simple. So in this case, we have two bodies, the float and the spar. And then we have a particle field connecting them together, and it's translational because this is going in a heave motion with respect to the spar. And then we have the global reference frame, the inertia reference frame. And this is also connected to the spar. Once we have these in place, we can go to the WEC input file and try to compare both of these together. I usually have them open side by side. So you just define the simulation file. So the simulation object, the first one is just the name of your Simulink file. It's called RM3. So this is the name here. And then you can turn on the visualization, simulation time, and the integrator, OD45, OD4, and the time step that you require. You define the waves that you need. And the good thing about the interesting thing about this examples, it also shows every other input you can use with waves. So if I'm running other simulation and I don't want to reinvent the wheel, I just go open these and copy and paste these lines from this simulation to somewhere else, and then modify the methods or the inputs here depending on my own model. And then you go to the body. We have two bodies. Body one, here it is the float, which is this one here. You can see it is here named body one, and also it's called body one here to make sure that these two instances from the body class are connected together. And the same thing for the spar. You also link the geometry from the STL file that I just showed. You define inertia, and so on. There are plenty of inputs. If you do right click and open the body class, you'll find multiple inputs that you can go through and explore at your own pace. And then we have the constraint block. This block here, if you don't click here, you'll find constraint one. This is linked together here. And also the power takeoff class. Also, these two are connected. So in order to run this, you just make sure that you are in the correct directory that has the WEC input file and has the Simulink model, and then you write WEC sim. Use camel case for this. Then press enter. It will take slightly longer time because I'm enabling the visualization, which is enabled by having Explorer on and off here. Yeah, and voila, you can get a visualization of the model that you have. Usually when I'm running the model the first couple of times, I will have the visualization on to make sure that the bodies are behaving as expected. Once I'm sure that they are connected correctly and related to each other, I start disabling this visualization and do my own thing. Like unless I want to do a presentation or something that I can just save this as a video. And these are the inputs that we have. It's a regular wave, but in this simulation, I'm enabling the XY large motion. So this RM3 is kind of will be drifting in the X and Y motion. That's why you're having this tapered shape. So with this, we can go to the next part of the presentation, the WEC sim applications. So we will go through some of the applications we have, like 5 applications or some of the advanced features. The first one of them would be the nonlinear hydrodynamics. This feature alone makes WEC can be a mid-fidelity solver because it can go from the linear wave theory to the nonlinear hydrodynamics. And also, we will pass through the QTFs. It's a newly added feature. The documentation, we're still working on the documentation for this. The quadratic transfer function is basically the second order forces. And then we will go through some of the advanced features for the inputter columns and generalized body modes, which can simulate flexible devices. Kelly will then take the lead and simulate the MCR, how to run multiple cases in parallel, and also how to parallelize your code. We'll also go through the simulation for offshore wind turbines through MOST, and then some of the capabilities related to the Steamscape and the power takeoff unit systems that's part of the WEC. So to enable the nonlinear hydrodynamics, you need 2 things. The first thing is a fine mesh. You have the STL file. It has to be an ASCII format, not binary format. And just you need to have a good mesh. A good mesh means that it has to be fine enough and the aspect ratio is not too small and the skewness level is below 0.25. Just a good mesh. And then the second thing is just to modify the instant of the body to just include this feature, whether non-hydro equals to 1 or equals to 2. The nonlinearities in devices arises from 2 things. The first thing is through the wetted surface area, which is related to the hydrostatic nonlinearities. If your body changing, the submerged part is changing like this because due to large motions or due to high wave steepness, you can enable these nonlinearities to capture it. So the first type of hydrodynamics, nonlinear hydrostatic restoring forces, is enabled by turning on this option and setting up to 1. The other one type of nonlinearities arises from this projected area, this black area up there. So if this is changing a lot like this, that you can see in this case, then also you need to account for the nonlinear excitation forces, like the nonlinear FK forces. And basically, you will be having this equals to 2. So having this equals to 1 will enable this first item. Having this equals to 2 will enable both of them. And this is very helpful. We were able to, in some papers, to validate that WEC performs very close to high fidelity solvers like SPH solvers and CFD solvers. For the second order excitation forces, or the QTFs, this is important for large structures. Large structures can be offshore platforms or rigs, floating offshore wind turbines, can be for ships as well, because there are some papers out there that use WEC to simulate ships, and also can be used for all sorts of other structures that can affected by the drift forces and second order forces. So basically the QTFs account for the interaction of waves together. So if you have omega 1 and omega 2, 2 frequencies in the same wave and they are interacting, this feature will be able to capture it and calculate the excitation forces based on it. And you can see here, this is an example case for an offshore floating wind turbine. And you can see here the dotted blue line, this is with the QTFs enabled. With the red line here is without the QTFs. So the QTFs will be able to capture some high stress loads on the structure that will not be captured without it. And basically it's enabled by setting the body.qtfs equals to 1, as simple as that. In the next month, we will be enabling, allowing some other methods for the calculation of the QTFs, the Newman approximation, the Stanley approximation, but the currently implemented one is the most accurate one. We will just include other things just to make sure that we satisfy all the user's needs. But with QTFs equals to 1, this will enable the most accurate, the most like state-of-the-art method for calculating it right now. We used a method similar to the one done by an OpenFast. And this is the validation between the calculation for the QTFs from the OrcaFlex, WEC, and FAST. And you can see pretty good matching for the fast varying component and the slowly varying component. The other method, the other advanced feature that we'll pass on now is how to simulate a flexible body. If you have the body that is behaving like this, it doesn't have a fixed shape. It's just hyperelastic material. So you can simulate these devices with some assumption that you don't have like very large deformations. There are some features that can do this large deformation that was implemented recently, which is a variable hydro, but we won't be covering it now. So you can see here, this device here can be, it's a spherical device. We can assume that this is the initial shape, and after deformation, it had a new shape. And these are the mode shapes that we have for this device. These mode shapes can be included in the solution and solved for. So you still can be able to simulate these kind of devices in the WEC sim. This also GPM feature can be also used when simulating oscillator columns. There are three main methods to simulate oscillator columns. The first method is to assume that you have two bodies here, the structure of the oscillator column, and you can assume that the body, that the water inside it is a second body. And you can do the simulation based on this. This is easiest to use, but it's not the most accurate. The recommended one is using the generalized body modes, which you would assume that the water surface here has mode shapes. It can be a heaving mode shape, it can be sloshing mode shape, it's whatever relevant to your case. And WEC sim can simulate both of them, plus also the free piston method, which is a WAMET unique feature. It can also handle this kind of like modeling for a single water column. So Kelly will jump in now to go through the PTO and the PTO sim and the Simscape toolboxes.
All right. Thank you so much, Mohammed. All right. Can everyone see my screen? Not letting me present. Give me a second. There we go. All right. Can everyone see my screen? I'm going to assume that's a yes. All right. So thank you so much, Mohammed, for talking through some of our applications. I did provide the link in the chat if people want to see some of those WEC sim applications. They are extensive. We are just highlighting a few. So I'm going to talk about how we model power takeoff systems in WEC sim. So I think we've focused a lot on how WEC sim solves the hydrodynamics and some of the hydrodynamic theory behind that, and some of the ways that you can add different nonlinearities back into the model on top of that fundamental boundary element method, solution, which is that linear potential flow theory based solution. So Mohammed, thank you so much for doing that. Now I want to talk about, once you've solved the hydrodynamics, one of the things that's really powerful about WEC sim is that you can model the power takeoff system dynamics. This power takeoff could be for electrical power and include a generator, or it could be to power an aquaculture system or a desalination system. So we have a set of PTO sim library blocks that are kind of built like plug and play library blocks to build things like hydraulic power takeoff systems or direct drive electrical power takeoff systems with existing library blocks. But additionally, users can couple WEC sim with any of the other MathWorks toolboxes, specifically the Simscape packages and MathWorks packages that are tailored to those needs. So many of the PTO sim blocks, they're actually a reconstruction of some of the Simscape blocks that exist in additional paid-for packages like Simscape Fluids or Simscape Electrical. But once you use some of these other toolboxes, if a user wants to pay for that additional license, it really allows people to extend WEC sim beyond just solving the hydrodynamics to actually modeling the component level of their energy harvesting system, whether that's to produce electrical power water, hydrogen. There are applications of it for all those things. Those cases that we saw for installations and deployments or crane operations or even hybrid energy systems, a lot of those really lean into some of the inherent MathWorks toolboxes that are not necessarily custom to WEC-Sim. So on that note, I'm going to focus on the WEC-Sim related toolboxes, which are the PTO blocks and the PTO Sim library. On the left-hand side, you'll see the hydraulic power takeoff system, like a notional power takeoff system. You see that there is a float that is subjected to wave motion. That wave motion is moving the float up and down. That's driving a piston. That piston is then pushing water through rectifying valves that go through a high pressure accumulator. And then the difference in pressure between the high and low pressure accumulator drive that hydraulic motor, which is then coupled with a rotary generator, which produces electrical power. So everything in this dash blocks, and actually even this, I should extend a little further to include that rotary generator, those are actually WEC-Sim library blocks or PTO Sim library blocks. And on the right-hand side here, you can see this is a PTO model in WEC-Sim. This on the left-hand side, that's your piston. You've got the rectifying check valve, the high and low pressure accumulators, the motor, and then the generator. So I'm actually going to show you an example. I've actually already run this case in the interest of time for you all. This is on the applications repository. It's the PTO Sim RM3 compressible hydraulic power takeoff system model. So on the left-hand side, we've got our input file, just like Mohammed showed you. It has all the same components that he already talked through, the simulation class, the wave class, the body classes, and the PTO. What's new down here are all these PTO Sim initializations, and these correspond to PTO Sim blocks that are in the WEC-Sim model. So the right-hand side is the Simulink model of the reference model 3, exact same case that Mohammed went through in his example, but instead of just applying a linear damping coefficient between the float and the spar to just have a linear assumption of your, oh, sorry, that was I don't know what I just did, a linear model of your PTO, you can actually go into this PTO system subsystem and you can see that we're actually modeling the component level of this hydraulic power takeoff system. Furthermore, what you can do once you have modeled the component level of the power takeoff system is you can actually start to implement real-time control and advanced control algorithms. So WEC-Sim allows you to model those complex PTO systems and also implement control in them. So also like Mohammed showed you, you can visualize the simulation, we can change the way that we're viewing this, like the aspect ratio. Sorry, I'm doing a terrible job moving this around real time. But you can watch the body float move in response to those waves. And the other thing that you get as a result of that is the time you can extract data at each of those component level of the PTO model at each time step. So this first figure, we're looking at the pressure in each of the high and low pressure accumulators. In figure 2, we're looking at the PTO force, which is the forcing on that PTO system. Figure 3, this is showing the motor or generator speed. And then figure 4 is showing the pressure differential on the hydraulic motor and then the hydraulic motor flow rate. So, these are just kind of some examples of things that you can get on the output of a PTO Sim model, which is, a somewhat unique capability within this space as compared to some of the other tools that were commercially available at the time when we developed WEC-Sim. So, and like I said, something that's really interesting about this is those are just some of the bespoke WEC-Sim models. You can do more once you move to implement some of the MATLAB toolboxes. So most is the next example I want to highlight, or the next application I want to highlight. So I mentioned, WEC-Sim was originally developed to model wave energy converters. That's our scope. We're funded by the Water Power Technologies Office. But there's a lot of examples in the literature of people applying WEC-SIM for other applications, including offshore wind, floating offshore wind, and hybrid energy systems. So we were fortunate enough to have people from the More Energy Lab in Italy who built upon WEC-SIM and created a toolbox that they called MOST, which is a set of library components, a wind turbine library, a wind class, building blocks to model offshore wind systems in WEC-SIM, and they built that on top of WEC-SIM. So they reached out to us and they said, hey, we'd really like to include that in the WEC-SIM source. We have it independently released, but we'd really like to work with you and build this capability. And we said, okay, that's great. With WPTO's blessing, we were able to collaborate with them, and they essentially maintain the wind side of this library, and we focus on the hydrodynamics. So I've also pre-run this case here. So on the left-hand side, you can see the input file for the MOST example, and everything to lines about 50 is all baseline WEC-SIM. Nothing special here, simulation class, wave class, body class, mooring, but lines 51 to 70, that's the, 51 to 70, those are the wind turbine specific class parameters and the wind class parameters, which are defining the input conditions and the wind turbine system. So just like I showed you under the building block of the PTO-SIM model, if I go into this wind turbine block model on the subsystem level, you'll see, and I'll make this really big, this is our wind turbine model. So you've got a tower, the nacelle, your rotor, a hub, and the 3 blades. So obviously, the way that this is constructed, it's assuming that you have a 3-bladed horizontal axis wind turbine. However, this could be modified. It could be amended to have different archetypes. Again, that's not our purview. That's the MOST team's development space, but we work with them to ensure that whatever updates they do on the MOST side get incorporated into the WEC-SIM source. And we're actually working on a publication with them right now that compares the MOST implementation with some other solvers for floating offshore wind applications. So I also just wanted to show kind of what this simulation looks like. You know, we saw a video of it in the screen. Obviously, it's running a lot faster than real time, 64x. Here, I can slow it down. There we go. Here's 1x. So you can start to see how the offshore wind, floating offshore wind turbine, not only how the rotor responds, but you'll see if you really pay attention in here that the platform is also moving in this case. So the input parameters for that is, you know, we've got the wind speed at the hub height as an input that's driving the rotor. We also have a wave surface elevation, and while you can't see it in the SimScape Explorer view here, you need to recognize that this platform is actually being subjected to waves. And then another thing that you get out is, you know, the power that's actually produced by the wind turbine. So that's just like, you know, kind of a atypical use case, I'd say, beyond wave energy use case of WEC-SIM that we've supported. But again, we're not the specific feature owners for that capability. That is actually the More Energy Lab. Okay, and then lastly, and I know we're a little over time and per hour, but that's why it was a notional schedule. Last thing I want to talk about, every single thing that we've talked about, those are capabilities within WEC-SIM. Those are ways that you can apply the software. But the thing we haven't talked about is, let's say you want to run a bunch of cases, whether it is one specific model that you want to run for a variety of different C states or damping coefficients, or let's say you want to do a design space exploration study and you want to study a bunch of different shapes or a bunch of different configurations. You need to be able to set up batch runs to do that, right? You don't want to have a human in the loop running every single one of those cases. And ideally, you also don't want to be doing it on your laptop, right? You want to do that on an HPC machine. So we have two different ways of doing that, both in series and in parallel. WECSIM MCR is the command that executes what we call the multiple condition run of WECSIM, which is the version of WECSIM that runs in series. There are three different ways that can be specified. Option one is by specifying a range of parameters in your input file. So I've also got this case pre-run. Here is, oh, not that one too far. Here is an input file that does that. Do you see lines 15 and 16 here, where we've got the wave height, where we're going from 1.5 to 2.5 meter waves by an increment of 1, and we're running wave periods of 6 to 8 second wave periods by an increment of 2. You can also iterate through your PTO damping. So here's another instance on here, line 39, going through a range of damping coefficients. And so what that does is it allows a person, a user, to just go through and type one command, which is that WECSIM MCR, and it will actually go through a batch run of each of those cases. So if I scroll through this command window, you'll see executing WECSIM. It's creating a case directory, WECSIM MCR case 1, and it's running through each of those parameters all the way until we get to WECSIM MCR case 8, and then it saves each of those cases output files in your case directory. So each one of these .mat files corresponds to each of the different cases. So that's option one. Option two is basically the same thing, except for instead of having your sweep of parameters defined in the input file, they're actually defined in a SLX file. And then option three is the one personally that I utilize the most, which is the one where you are actually specifying the MCR cases in a workspace variable. So here you've got a header that specifies the variables that you want to change. In this case, it's wave period, wave height, PTO damping, and PTO stiffness. And then you have the values which specify those parameters. In this case, we're actually not changing stiffness, but you can see the wave height, the period, and then the damping coefficient. So these are the exact same cases run 3 different ways using WECSIM MCR. Again, the way you execute that is just typing WECSIM MCR in the command window. And then in terms of outputs, I think they actually were on my first screen, unfortunately. You can get, here we go, some power matrices. Here's some example power matrices. So in this case, we're looking at, just for those 8 cases, those 2 periods, 1.5 second period, 2.5 second period, and a wave height of 6 and 8 respectively for the damping, the 2 different damping values. So you can start to populate power matrices for this. Again, I didn't run this real time right now, just in the interest of time, but these cases do run pretty quickly. If you're not happy with how long it's taking, you can also use WECSIM PCT. It's the exact same setup, those same 3 options, but instead of running those cases in series, it actually runs them in parallel. The caveat being that you have to purchase an additional toolbox. It's the MATLAB Parallel Computing Toolbox. This is the reason that we support both. We're really mindful about the fact that WECSIM does rely on these paid packages, and we try to minimize the amount of package requirements for our users. So if there's a way to do something without adding additional cost to the users, we try to do that, or at least support it. Okay, with that, that's the end of our presentation. So thank you all for your time, and I'm going to pass it off back to Megan.
Thanks, Kelly. Well done. Do you mind sharing those slides again? Perfect.
Yep, sorry about that. I realized that after I stopped sharing.
No, don't worry. So that concludes the WEC session. The next session will be OpenFast on April 23rd at 11 a.m. OpenFast, Moredyne, MHKit, and WECUp tool will be utilizing CoCalc, which is an online collaborative software. Next slide, Kelly. So we ask that you please make your CoCalc account before the demo day. You can create either a personal or a professional account. It doesn't necessarily matter. The one thing that does matter is that you share the account email that you used to make your CoCalc account in chat now, or you can email it to Kelly later. Also, if you can just navigate to the Your Projects tab once you get a confirmation that you've been added to the Demo Days project, you should see either WPTO Software Demo Days or your name - Software Demo Days. Next slide. All right, just reiterating this from the kickoff again, you should have access to the series of events. If not, please contact us. We ask that you accept the meeting invites for the sessions you plan to attend. Some people have been having issues with this. Just a reminder, you have to save each meeting attachment, and then from there, you'll be able to copy the meeting invites to your calendar through the saved files. Again, create your CoCalc account, share your email with us, ensure that you have access to the Software Demo Days project. And on demo day, you can test out your CoCalc account, make sure everything's working, you have access to the different folders within the project. Everyone did super well today, but make sure that you have your video off and mic off for the duration of the actual demo, and then at the end we'll go into Q&A where we can interact, unmute, turn on our cameras and everything. This is being recorded now, and it will be for each session moving forward, so just keep that in mind as well.